happy to introduce and also happy to introduce him to those of you that have not yet met him, although I know many of you have read his papers. So James Gleeson is head of the Department of Mathematics and Statistics in the University of Limerick in Ireland, and also the director of the Science Foundation Ireland Centre for Research Training in Foundations of Data Science. Did I say that correctly? James got a master in mathematical physics in the University of Dublin, University College Dublin, and a PhD in applied mathematics at Caltech in California. His research interests are in mathematical modeling of stochastic systems with special focus on complex systems and complex networks. And he has very high impact contributions on dynamics of complex networks that many of us have enjoyed reading a lot. So thanks for being here. The floor is yours, James.
Thank you very much. Thank you, Maxi. It's a great pleasure to be here. It's my first time in Mallorca, which is a shame because I've known Maxi for a long time and very, very, very impressed with IFISC and all its works throughout the years. So it's great to have the reason to be here, and thank you for the invitation to give a seminar while I'm here as well. I'm conscious that you have two seminars this afternoon, so I'll try and keep this one relatively light, and I'll leave some time for questions at the end. So hopefully I won't run too long. What I wanted to do was to give you some, I really want to talk about branching processes, partly because I know I'm in a group of physics and applied math experts here, and I think there's lots of interesting things to be done in this space, which is a little bit different than maybe some of the stuff I did a decade or so ago. So let me start off perhaps by motivating some of the things that we've done. In the prehistory, before we did this type of work, we looked at dynamical systems or master equation type approaches for dynamical systems on networks. While doing that, I was noting some results of empirical work on Twitter. So this isn't from our group, it's from two other groups, Christina Lerman in USC in particular, where they've looked at the size of outbreaks, quote unquote, if you think of these as infection events or of viral memes on Twitter. So these are both data sets taken from Twitter. The basic idea is that they take a large data scrape, they identify a particular tweet, and then in the rest of the data set that's quite long time-wise after that, they identify how many times that tweet has been retweeted. Okay, so if this is a data set about things going viral, relatively old data sets, has to be said, but these are distributions then of the what we'll call the cascade size or the tree size, or the outbreak size, if you want to think in terms of infection events, for different individual tweets. So, and these are densities, so counts, if you like. So just frequency of how often cascades of this size are observed in these large empirical data sets. And what you see is that most of the time, nothing happens. So a tweet is sent out there and it's never retweeted. Okay, and that really is most of the time. This is a log scale, so it's sort of an order of magnitude larger than any of the other events. Is that, and it's hard to see, but it's also the case here that the event of size 1 or the single tweet is the dominant behavior. However, if things are retweeted, there is a possibility that you can get some very, very large events, and you can get those with probabilities that scale, one might argue, roughly like a power law. I'm wary of claiming power laws, but you can see here for comparison, I've shown the Pareto or the power law distributions on these log plots that would correspond to a scaling exponent of -1.5 or a scaling exponent of -2. So you can see if you imagine that this is power law, the slope is even less steep than -2. So that's a very fat tail. Okay, technically, if this power law was to continue forever, you'd have a distribution not only whose variance is infinite, which we're fairly accustomed to in thinking about network degree distributions, but its mean would actually be infinite if the exponent is in magnitude less than 2. So these are very fat-tailed distributions, and one of the things I wanted to do was to think about modeling of these. In previous work, I've largely thought about the fraction of nodes in a network that take on a particular behavior, or me and of course many others. But the tools I came to on this really were not adequate here, because viral events, viral outbreaks 10,000, maybe 100,000 retweets, but there are billions of people on Twitter. So as a fraction of the network that's taken over by this event, this is actually still a very, very tiny fraction. The kinds of tools that we had previously weren't adequate to try and describe distributions like these. So that's kind of historically what led me to this line of modeling. I'm putting this in proper chronological order too. So to give credit to the Indiana group, Phil Menser, Flamini, Vespignani, and Lillian Wang, who was the PhD student, I think, main author of this work. This appeared before the work I'm about to show you, although we were unaware of it at the time. And what they did was they tried to build a model that reproduced some of the features of these, let's call them popularity distributions or meme size distributions. So they had a model where each node on the network was a person, and that person was exposed to incoming tweets from people that they followed. And they had a memory which kept track of things they'd seen in the recent past, and some rules about whether they would, how they'd post that that meme onwards. And again, similar kind of empirical data that they've seen. These are now CCDFs, but still have the same kind of heavy tail distribution we've seen before. And what they did in this work was to build a model, a very simplified version of which I'll show you in a minute, which roughly produced that sort of behavior if they put in the network structure that corresponded roughly to what real Twitter network looks like. So I'll explain some of that again in a second, but not if they put in a random network. And this model was sufficiently complicated that it could really only be studied numerically. So again, unaware of this, but thinking about questions of this type, my then postdoc at the time, Jonathan Ward, who's now a lecturer in Leeds, came to me at some time, I don't know, a year or two prior to this, suggesting this model. Okay, so and the reason I'm showing it to you now is because it's roughly analytically tractable. If we use branching processes, we can learn a lot about what's going on. It's considerably simpler than what's in the Wang et al. Model, although it can be extended in certain ways. And it has some nice understandings that relate us to physical models that you're maybe more accustomed to. So I think you might like to see them. The model is pretty easy to describe. So I'm going to show it to you in kind of cartoon form. Let's first start off by giving ourselves a network structure. So here's a network. I'm going to, and these are, again, users on Twitter, followers, Twitter user accounts. And I'm going to put the arrow in the direction of which the tweets travel. Again, there's different conventions on how you draw arrows in this directed network, but I'm going to put the arrows in the direction that the tweets travel. So this node here is a follower of this node here. And when this node tweets, the information will end up on being exposed to this person here. We're going to assume there's a large number n of nodes, and I should have said we'll assume that each node has, we're going to assume we have the followers degree distribution, the out degree of nodes. We can do various things with the in degrees. I can talk about those later if you wish, but for now, let's just assume that we know the out degree of nodes, and we do a configuration model type of random wiring to get the in degrees. In terms of dynamics, we're going to give each node a memory screen. So these little things are screens, and on the screens, there are typically one thing that each person can remember. So again, I said it's a very simplified model. It's a hopefully oversimplified model of how real Twitter users behave, or ex-users behave nowadays. So these people can think about exactly one thing at a time. That's the meme of current interest to that node. I like to draw the screens with colors on them for different memes. So these two people are thinking about the same thing at this time. And each screen has capacity for only one meme. We'll do sort of standard discrete time stepping, which I'll talk about continuous time in a little while, but let's just take our time in small increments of time 1/n. So on average, each node updates once per unit time. We choose a node at random, and with a certain probability, so going to choose this node in the current time step. With probability mu, we're going to let that node innovate. So an innovation is the creation of a new meme, which wasn't previously in the system, and the tweeting of that meme to all the followers of that node. Okay. So that happens with some probability mu. The converse probability with probability 1 minus mu, so let's set up the same system, the same node is chosen, but now instead of innovating, it just retweets what's currently on its screen. So the meme that's currently on its screen gets broadcast out to the followers again, and again overwrites what's on their screens. And that's it. Okay, that's all we do. So one of the things, again, Christina Lerman's group in USC has talked about this for quite a while. This looks like a simple contagion model, but there are differences between standard virus models and the behavior of standard virus disease spread models and some of these things as well. And we're trying to model the attention economy, if you like, the cognitive limits, the fact that we can't hold multiple things in our head by the fact that there's, in this instance, one meme appearing on a screen each time. And when this blue meme benefits by being broadcast, some other meme, in this case, the red one or the green one here, must suffer because of the competition. Just to give you some nice visualization of it, again, this is from John Ward, who's, as I said, now in University of Leeds. If we think of all the screens in the system, and we just line them up here as a vector and color them by according to the meme that's on them, and we let time run forward in the model, again, we've taken some artistic liberties here in the sense that we've grouped together the screens that have the same meme on them, so you can kind of see the patterns emerging. In reality, this will be very multicolored and not quite as banded, but you can see the competition killing off, for example, some of the memes. So if something disappears off the screens, it's eventually gone. I don't know if you can see an innovation event. So you see new memes arising and growing, and the entire system continues to churn indefinitely in a sort of a dynamic equilibrium. If we look at individual memes, so if we take, and this is all from numerical simulations, if we take the popularity of a given meme, which is just the number of times it's been tweeted, you typically will see some sort of growth over time of the popularity of a meme. Here you can see a growth and then an event that accelerates that growth. But all memes eventually must face something like this, which is where they have been tweeted a good number of times, but eventually the competition in the system will cause them to be wiped out. So they've disappeared off every screen in the system. That meme is now no longer existing and therefore can no longer grow in popularity, and it is saturated forever here. However, you often will see things like this where you'll see growth, apparent saturation, but it actually hasn't disappeared off every screen in the system. And if that meme is lucky, it can revitalize and regrow. And here again, you can see it almost saturates and then grows again. So there's quite rich, and again, if you look at the numbers on the vertical axis here, it's quite varied distributions of popularities that can occur. To jump to the punchline on it, I suppose this is the punchline from the paper probably. If we plot the resulting popularities of those memes, so going back to the empirical data I showed you at the start, if we imagine we're tracking how many times a given meme has been tweeted, here we've added the age of the meme. So, and I didn't talk about that here, the age of the meme is the time since it first appeared in the system. So remember, there's this innovation event that can cause new memes to appear. When they appear, they then have an age that grows older. So if we look at the relatively young memes and the distribution of their popularities, it's fairly thin-tailed, but as the age gets larger, if we look at memes that have been in the system longer and longer, their distribution is approaching, again, a -3/2 power law with an exponential cutoff, which is probably quite familiar to those who've looked at self-organized criticality and other types of models like these. I should clarify that this is on a network where we've assumed that every node has exactly 10 followers. Okay, so a very non-Twitter-like network, if you like. And we've set the innovation, in this case, to 0. Normally, we just keep the innovation rate pretty low, and we see results like these. Over here, by contrast, is a degree distribution that is more like real Twitter, which is a heavy-tailed power law out degree distribution or number of followers distribution, with so -2.5 power law. And there you again, in the large age limit, will see a power law distribution of the popularities, but the exponent here is different than the exponent is here, and in fact is closely related to the gamma there. And I'll talk to you a little bit about where these theory lines come from in a second, because that's the branching process piece that I want to get to. Two things to note that I'll come back to. I introduced the model as discrete time, but if n is large, we can turn it into a continuous time Markov process where all the screens become active at rate 1, as long as n is large enough. I think that's fairly obvious and probably familiar from similar types of models that you've seen on networks before. And the main qualitative feature, so that this existence of heavy-tailed popularity distributions are quite robust to some of the generalizations that I'll mention in a few minutes. among them being if the screens can hold more than one thing at a time. That's not crucial to this. You can get extensions of it, or if people can look further back in time to remember things, or if we have some correlations between in degrees and out degrees and so on. So all those things are quite robust. I suppose one of the main points was that it is interesting, I think, that you can get these heavy tail distributions of meme popularity even without putting in a heavy tail network. So you might remember when I showed you at the start, the Wang et al., the Indiana group had successfully reproduced empirical types of popularity distributions, but they did have to put in empirical types of networks. So they put in these types of networks, whereas when they did the random network, they weren't getting exactly this type of thing. So that was one interesting thing. I said there are various extensions. I won't go into them in any detail, but if, for example, we allow continuous time, we have a model where the users can look backwards in time with a certain distribution of how far back in time one might look. This is a plot of their timeline that at any given time, they might look back and choose what they're going to retweet at different moments in time. And the sketch here is just to introduce you to some of the branching processes, which I'll get to in a second. Okay, so that's by way of motivation and introduction. I want to talk about branching processes quite a bit. So again, I'm assuming people here have a good familiarity with them already, but if you'll indulge me, I'll give a brief recap of some of the main topics that we need. And we can do pretty much everything we need in discrete time. So your classic Galton-Watson branching process is one where we have an object. We'll often call them particles, but in this instance, it would be a tweet event. And we count the generations so that this is a parent of these, in this instance, 2 children of the next generation. And then this one subsequently causes 3 more, let's say, retweet events, et cetera, et cetera. The ingredients of a classic branching process is just the probability QK that each particle will, in the next generation, have K children. Okay, so you put a probability distribution as an input to a branching process, and as an output, you get realizations of these things. And some of the questions people ask are, does this branching process go on forever? How many nodes might you expect to find in one realization of this, or with what probability? So what's the distribution of, let's say, tree sizes for this kind of thing? Couple of terminology pieces. We'll talk about the branching number, which is the mean of the offspring distribution. It's the expected number of children that a parent will have. Okay. These days, I remind people that's more or less the definition of R0 for COVID or any other disease. It's the expected number of secondary cases. These are secondary infections from each primary infection. And it's the mean of the offspring distribution. So the offspring distribution itself can be quite wide, but the most important number is the mean. And it's well known, of course, that the critical case X=1 separates the subcritical from the supercritical cases. Supercritical branching process may go on forever. A subcritical branching process is guaranteed to die out in finite time. It turns out that in our models, the branching number for a meme is 1 minus mu, where mu is the innovation probability. So you remember this probability, which I said in most of our examples was quite small. That's the probability that a user will generate a new meme rather than retweeting what's currently on their screen. It means that our models are destined to be subcritical, right? Because mu is small but positive. So this is definitely less than 1. So we're definitely in the subcritical regime. And I'll talk more about that one later too. So that essentially models of calculating the size of the distribution of sizes of these trees is what gave us these theory curves here. Again, just briefly reminding you some of the things you might need for that. So this is if we know a probability distribution or probability mass function, for example, the offspring distribution, we often find it useful to define these things called probability generating functions, or PGFs, which are really just taking the elements of that probability distribution and using them as the coefficients in a power series to generate this function f of x. Why would we do that? Well, it turns out to have a couple of useful properties. For example, if I evaluate this f at x=1, I sum up all the probabilities and I must get 1. If I differentiate this function with respect to x and then plug in x=1, I'll pull down a power of k. I'll set x to 1, leaving with k, qk, giving me the mean of that distribution. And remember, the mean of the offspring distribution is the branching number. So that's one reason to use PGFs. They have some nice properties that allow quick calculations. But more useful is the notion that, and again, I guess here you're probably accustomed to Fourier transforming or Laplace transforming certain equations if you need to solve them. This, I often introduce this as being similar in principle to that. You start in a space where we have this infinite series of objects here, and it's sometimes useful for us to move to a transform space, in this case, where there are functions of x. Why do we do that with Fourier transforms? Because the operations on our original complicated equation are complicated in this space. They're easier to operate over here. And we'll see that there are easier operations for probability generating functions that are useful to us. But in the end, if you remember from Fourier transform or Laplace transforms, you kind of always face the problem of going back from the transform space back to the original physical space. And that in doing that, you need some sort of inverse transform, which again, won't go into details here, but often in this instance requires numerical methods, which are known largely from queuing theory, in fact, and rely on fast Fourier transforms. So for now, if you'll just take it that we can go from the space of probability distributions or probability values into the probability generating function space. And here's probably the most useful reason for doing it, is that if I'm going to add two independent random variables, which come from two distributions, or equivalently, if I have their generating functions, the probability that the sum of those two random variables is a number k is distributed with the generating function, which is gotten by multiplying the generating functions of the two pieces I'm adding together. Okay, so in the simplest example, undergraduate example, if I'm rolling two dice and I'm asking what's the probability that I get 7, or the probability that I get 10, or the probability that I get 12, those probability calculations I can do by writing in the generating function for the dice, which is 1 over 6 plus 1 over 6x plus 1 over 6x squared plus 1 over 6 all the way up to 1 over 6 x to the power 6, and multiplying it by the same generating function because I have two similar dice, and then reading off the powers of x to the k, the coefficients of those. Anyway, again, if that didn't make a whole lot of sense, just take it that the generating function is a useful tool for us in some of the calculations that we'll need. Why do I care about adding random variables? So the best way for me to show you that was to take a trivial and non-realistic example, but let's suppose every parent has exactly 2 children. So a generating function where every parent has exactly 2 children, right? It's easy to draw and it's easy to do the calculations. How then do I calculate the number of nodes or number of dots in this big blue box? Well, the assumption of a branching process is that I get a IID processes, that these children are IID processes. In other words, that they're independent and identically distributed. So they are, of course, stochastic processes. So in the end, I'll actually have different numbers of nodes in each of these yellow boxes, but the same probability rules apply to both. So if you think about it, this pink node is seeded at time tau, and here are 2 subtrees. And again, a major assumption of branching process is that these trees remain independent from each other and don't disrupt each other. So when I observe at time omega here, I'm going to have the blue box contains all this node plus all the nodes in the yellow box and all the nodes in this yellow box. So if I define G to be the generating function for the size of the tree, which in branching process is often called the total progeny of the process, seeded by this particle at time tau, what I'm going to express G, what I'm going to say is G is made up of 1, this particle here, plus the number of particles in this yellow box, plus the number of particles in this yellow box. Okay, which, again, remembering that when I add the random variable that tells me the number of particles here to the random variable that tells me the number of particles here, I'm adding 2 random variables with the same distribution. And I told you that the generating function that will be gotten by multiplying the generating function by itself. Okay, so I'm here have a squaring this generating function for the yellow box, and I'm then multiplying it by x because I want to add 1 particle here, this parent particle, into my count. So this is the sum of the sizes of 2 yellow boxes, and this x gives me 1 more power of x, which adds 1 to my count to get the total size of in the blue box. And if I've written this in terms of a seed time and an observation time omega, but if I go down to the age of the trees, this tree, when it's observed, has age n, the blue box, and I have 2 age n minus 1 trees in the yellow box. So again, you see this formula here, which is a fairly simple recursive formula. Now, that was in the unrealistic assumption where everyone had 2 children. More realistically, each node has k children with probability qk. Okay, but the same kind of argument applies. So without without making too much of a deal of it, again, the number of particles in the blue box is made up of 1, this one, which I'm going to put in with the power of x, plus the sum of the particles in however many yellow boxes I need here in generation 1. So with probability qk, there are k such children. So probability qk, there are k copies of the yellow box, and I need to sum that over all possible values of k for that first generation. That's where this sum is coming from. Notice this is qk times this thing to the power k, which is precisely the definition of the generating function, right? It's the sum of the probabilities times something to the power k. So that's the generating function evaluated at these later born generations. Again, in terms of the ages of generations, that's gn is given recursively as x times f of gn minus 1, where g is the tree age. And I can start off, because I know that if I just have one particle at the start, I just have x to the power 1. So given g0, I can get g1, and so on, and recursively get this. Okay, so that's a classic argument in branching processes to allow us to calculate the distribution of sizes of trees given the offspring distribution f. And that's precisely more or less what we did here. Slightly more complicated because we were assuming continuous time, but in its essence, that's what gives us these black curves here. We have this index for the age of the trees, which allows us to do different curves for each of the different distributions for memes of different ages. I already told you that this asymptotically gives us a 3/2 power law with an exponential cutoff, and this one gives us a power law distribution with a power law driven by the underlying out degree distribution of the Twitter network. So these are familiar, hopefully, to some of you. They're self-organized criticality mean field results as well, because it's the same type of dynamics that's essentially driving it. Except this isn't really self-organized. It's organized by the competition. And it's crucial for these results that the mu values here are small. So you can get these asymptotically, but you do have to have small rates of innovation. So in a universe where people on Twitter mindlessly retweet instead of generating new and innovative content, you might expect to see fat tail distributions. You can decide for yourself if that's the case or not. I said we did some generalizations. One of the generalizations was this one. This was with Yamir Moreno's group in Zaragoza, looking at some empirical data. So we actually got distributions for the popularity of hashtags, a large hashtag set, looked at them at different ages and compared them with these are the empirical curves. These are the model curves offset. And again, in that instance, we included the one I showed you, continuous time with memory over time and so on. So we got some nice results with that. Happy to take any quick questions, maybe, for any. Okay, so as you can see, that's all fairly old work. It's been around a while. Two common challenges. One is that you're assuming you have a branching process, right? And one of the strongest branching process assumptions is that those two yellow boxes I was showing you, that they are independent of each other and that they behave the same. And I didn't expressly say it, but as I go further and further through the generations, I'm still assuming that all the children processes behave the same. So we're assuming that there's this long time independence and identically distributed process. Is that actually really likely to be true on Twitter? I'll show you some empirical work in that in a second. And then after that, and this is still work in progress, but I'll show it to you at the end, these are all neutral models. So you might have noticed that the memes I was showing you were just colored screens. There was nothing inherently more attractive about any one of those memes to any other. So the ones that went viral and the ones that didn't, the only difference between them was pure luck. Some of them were luckier and ended up getting tweeted more. But one might argue that and this is a discussion I frequently have with people who do empirical data collection and are looking for maybe ways of predicting which memes become more popular than others. One would like to think that there's more than pure randomness in what becomes popular and what doesn't. So what happens if there's some inherent fitness advantage, or one meme is a little bit more likely to be tweeted than another? What difference does that make? So that's the second part of this that I want to get onto. Let me start with some empirical data. So this work was largely led by David O'Sullivan, who was a PhD student at the time and is now a colleague of mine in the University of Limerick. So we looked at two large-scale data sets. This one was from the Irish same-sex marriage referendum of 2015. where we gathered in the end about 31,000 cascade events based off searching for hashtags, which were the two most common hashtags used in the lead up to that voting referendum. And this older data set from Christina Lehrman's group in USC, which had about 63,000 trees, where they had looked at URLs and tracked retweets of URLs over time as well. There's a lot of skill/art in how do you reconstruct a tree. So how do you know what tweet actually caused the person to retweet something? So there was a paper by Goel, Watts et al. Who had a tree construction method. We've just used that in this instance. So it's essentially in both those data sets, what we have is an ensemble of cascade trees. So the first one, second one, we have 30 or 60,000 of them, and each of them can be laid out like this. There's a seed node or seed tweet, and then subsequent tweets that happen in different generations. And we can do things like plot the distributions of the cascade sizes. How did things go viral? Did things not? In similar ways to what you've seen on the previous work. I'm just doing these side by side so you see the comparisons. So the marriage referendum one, for example, was overall less viral event than some of these URLs, probably given the restricted size of the population in the Irish Twitter sphere. You can ask how many generations does a tree go through before it dies? So in these instances, you see trees of lifetimes up to 8, 9, 10, 11 generations. These URL tweets, again, went through longer and more sustained lifetimes. And you might calculate other aspects of the trees. This is sometimes something of interest. Are we interested in trees that are narrow and deep? So they get retweeted by 1 or 2 people each time, but that goes on for a long time, long number of generations. Or could it be a broadcast event? Someone tweets to 100 people, each of them retweets it, and then it doesn't really go any further than that. Okay, those might be trees with the same number of actual nodes in them, but very different shape or structure. So there are lots of different measures, but the average depth, for example, of a tree is one that you can plot a distribution for as well. One slight thing that we do need to take into account in this data set is that we don't just have, we're going to see if we can calculate an offspring distribution, but by the way that these cascades are gathered from the data, we only gather those tweets that are retweeted at least once, okay, just for sheer data storage problems. So the offspring distribution here is biased because we will always, the fact that it's in the data set means it was retweeted at least once. So you'll see that crop up in a minute. If we lay out all our trees like this and just count the number of nodes that are in each generation, in each tree, and use that to calculate an empirical branching number. So this empirical branching number is on average, the number of nodes in the next generation that are generated by each node in this generation. Over the generations, you can see, and I'm drawing the green line here to guide your eyes, to something that looks roughly constant. So this was a little bit of a surprise even to us. We thought that as information on Twitter gets propagated, time is passing, and one might imagine that the novelty of whatever information it was might wear off and that it would be less likely to get propagated further, let's say later in the cascade than it is earlier in the cascade. Now, you might look at these points and say that's what that is, but it's not. This is actually due to that biasing I was just telling you about on the data set collection. So that first generation is different. But once you hit somewhere into the middle of these plots, you can see that there's a roughly constant branching number. Which means when we look at the empirical offspring distributions, again, the black is the seed generation offspring distribution. So it's the probability of that first. So you can see there is no 0 offspring for that first case. And then the colors are for some of the other generations that are covered by these green lines. You can see that they are roughly very similar types of distributions, even quite late into the processes. So we fitted those distributions, didn't have to do this piece, but it makes some of the calculations, theory calculations later easy. Plugged it into this sort of approach that I've shown you already, and asked in the long age limit or the steady state limit, what is the distribution of tree sizes that you get? So again, remember, we're plugging in essentially an empirical offspring distribution. We fitted it. So not only do we see that the offspring distributions tell us that this does actually look quite like a branching process in the sense that the offspring distribution is remaining the same through the generations, but the outputs of that look quite good compared to the branching process theory, which would give us this for the tree sizes. I haven't shown you the theory, but there is corresponding theory for the lifetimes of cascades. And less theory on this, but the average tree depth we did some work on as well. And this is a Monte Carlo simulation in red, but we did some calculations around the actual average of that and found that they work quite well. So again, the data and the theory numbers are relatively close here. So keeping it short, I think the main point here was slightly surprising to us is that, yes, the IID children processes do seem to work pretty well here. To be clear, we really only checked the one of these eyes, so we haven't checked the independence of those children, and you might argue that that's important on networks where there's maybe considerable clustering or closing of loops. But insofar as it gives some indication that branching process models are more than just toy models in this instance and might be useful, I think it's quite interesting. I'm going to spend the rest of the time talking about going beyond these neutral models. So again, neutral models is a term from, I think, originally from math biology, where you might argue that's are all the memes equally likely to be retweeted, or are some more inherently likely to be tweeted? So in terms of evolutionary or genetic evolution models, you'd call that a fitness advantage. So again, looking back at some related work, and again, looking primarily to the Indiana group, they did some work on models with heterogeneous fitness. So again, I showed you the Lillian Wang model. This is an extension of it, where they have included a quality indicator for the information. So again, trying to make information that is, giving it an inherent number that is supposed to be its quality, and making information that is high quality more likely to be retweeted. Now, this paper had some problems. It ended up being retracted because of some issues with the model and the data mix-ups, but none of that is actually important to what I'm about to tell you. So just if you do look it up, look up the archive version, which has all the corrections in it. So what's in that paper, for example, is some results from their model. They had both empirical data, which is the black curve, and again, similar type to what we had before. And this mu here plays the same role as it does in ours, the innovation probability. So you can see as the innovation probability gets smaller, heading towards the red curve, you get distributions that are getting closer and closer to both to the empirical data, and I think this is just a guide to the eye rather than a fit, but it's a -2 power law. So they were seeing something that looked like a -2 power law. And I didn't stress it, but you might remember in our models, we were getting a -1.5 with an exponential cutoff. And on the other side with power law networks, you could get some things that, again, were between -1.5 and -2. But this -2 power law was quite robust in this case, where they had different quality information, which was intriguing, I think. Perhaps one of the explanations is from this paper, where an even older model for mathematical theory of citing. So this expressly has branching processes in it, and these are papers who cite other papers. They'd looked at popularity type distributions there and argued that if there's a Darwinian fitness that is different for each of these papers, you can end up with a -2 power law that's here. So I think that might be the kind of fundamental explanation for what we're seeing. But in terms of our model, we spent a long time trying to think about how could we include some element of fitness in a way that was still analytically tractable. So again, I should say in this model, this is purely numerical results, basically because the way they implemented the quality was people had to choose between all the memes that they'd seen recently, the highest quality one, in order to retweet that. So in our original model, when I described it to you, I said, if we thought of it as a continuous time Markov process, each of the screens become active at rate 1. So on average, it's just a Poisson bell rings for each screen, whether it's the tweet or not. And again, to remind you, you've seen this already, that I said the branching number for each meme is 1 minus mu, where mu is the innovation probability. And in particular, this is less than 1. But it's also the same for every meme, and that's the bit I want to change now. So every meme has the same branching number. So this way of adding meme fitness to the model, that I would credit postdoc Sam Unicombe with this for the original idea, and Shane Mannion's a PhD student who's just finishing and has done a lot of the numerical work on it. We are now going to allow each meme to have an inherent fitness. And the way that fitness is observed in the system is that it screens with that meme on it retweet at that rate. Okay, so if everyone has fitness 1, then we're back to the original model. But if if a certain meme is a fitter meme, we'll just give it a slightly higher rate. So that means it's a little bit more likely to be that people with that meme on their screen are a little bit more likely to be excited about it and a little bit more likely to retweet it. So it's the rate that screens with this meme become active. So we can put this into a rate-based model. And it turns out if you do the calculations for that, the branching number for meme I is now dependent on the meme, depends on the fitness of the meme, depends on the degree of the network, and it depends on the overall average fitness across the network. So it may not be obvious, but basically the important thing here is that we see a ratio of the fitness of meme I divided by the average fitness in the system appearing. And that more or less multiplicatively multiplies the branching number. So the original branching number of 1 minus mu is in here. And you can see that if all these phi's are the same, so that phi and that phi are the same as that phi there, we'll get z plus 1 dividing out the z plus 1. But more generally, the fitter memes will have branching numbers that are above average, and the less fit memes will have branching numbers that are below average. And I should say, to calculate this average is itself a problem. So what is the steady state average in the system? Well, that of course depends on the probability that memes that are born by innovation have fitness I. And again, this system continues to churn, and it's in a sort of a non-equilibrium state, dynamic equilibrium at least, where you can calculate this from a mean field type of argument to work out what that is, and then figure out the branching numbers for each of the memes once the transients have passed. So these are early results from Shane. So forgive the quality, but the basic idea is here is that we've just taken a model with two different fitnesses. So a low fitness and a higher fitness set of memes. So memes are born either with low fitness or high fitness. And then these distributions come from the numerical simulations with that model, with those as the rates. And the curves, again, come from an extension of the existing theory to show that we can get good matches between theory and simulation. And just over here is the calculation to get the average fitness across the system, as I said, through a mean field type of calculation. Depending on the different, and again, we only have two types of fitness in this model. You can get different distributions of fitnesses. But overall, what we'd expect and where I think this is going is that with a large distribution of heterogeneous fitnesses, that we can bring ourselves to a situation like this one here, which I believe will give us this -2 type of robust power law behavior that was seen in that model. So a lot later on, but I think we've reached some analytical understanding for what might be going on in models in general where fitness is important. I'm pretty much at the end, so I'll maybe stop and take some questions, but I'll leave you with some what I think are open questions still at this point. The age distribution of the memes. So you get some sense for we talked about the age of the memes and how their popularity can depend on age. But again, as this system works its way into some sort of dynamic equilibrium, what is the average distribution of ages of memes in the system? That's a calculation we're working on. Closer to reality and dealing with data is the questions of the non-heterogeneous nature of time. So in any of these social media systems, you can see a daily variation in the activity of people between the night-day cycle. And that presumably has some impact on how likely it is that things get tweeted or not. And it can have some interesting effects in terms of the branching number. So that's something we're looking at too. More general types of questions that people are interested in, of course, would be the identification of super spreaders from models like this or influencers. Again, you'll have seen in the model, a lot of it is fluctuation driven. So it's not impossible that both that memes can become successful or that people can appear to be influential when that may not be consistent over time. So reliably identifying them, I guess is what I should be saying here, is a more difficult question. And looking at the whole data question, I've talked briefly about inferring offspring distributions. And of course, the holy grail here is to predict the future popularity of tweets or other pieces of information, given perhaps some early exposure to their early behavior and allowing for things like diurnal or other fluctuations that might be influencing that. Again, that's a big open problem that lots of other people are working on as well. So I'll finish with conclusions just to say, I suppose, that this is an ongoing challenge. I think it's an interesting area. It does allow for some nice mathematical work, which is principally why I like it, but I think there's plenty of other challenges there that some of you might be interested in. Slightly to our surprise, the assumptions of branching process do appear to be valid in at least the cascades that we've checked. Nice analytical or quasi-analytical results, again, classic ones for branching processes and ones that we've worked on in other ways as well. And then just this recent work, which is yet to be published, but hopefully soon, the impacts of heterogeneous mean fitness. And I suppose from a mathematical point of view, generalizing these models and trying to take into account aspects that are not already in it or that are needed to describe the data is always a way to motivate new analytical approaches. So happy to chat to you if you have any questions on any of that or suggestions, and take questions now. Thank you.
Thanks very much, James. So questions?
I should have thanked my collaborators, by the way, and funders. So let me stick that slide up while we talk. Yeah.
Yes.
Thank you for a very interesting lecture. I have a question about quality of meme, because here it's like you have the quality of meme, the quality is high, and the fitness is high also in your model, yeah?
Yes.
Okay.
Well,
so if
let me say yes for now. I'll come back.
Yeah. So if the fitness is high, then the probability of survival is also higher.
Yeah.
So it can survive longer. Now my question is, how do you define the quality of meme? Is it just the definition of the quality? Because you know probably what I mean. Because sometimes you could think about quality as if it's false or if it's fake.
Yeah.
If it's true, whereas probably the length of living is not so much, or maybe it is, I don't know, correlated to.
Yeah, that's a good point, and I should have been clearer. I think so. All I think we are explicitly doing is putting a fitness into the model as it is. So quality, while it's a motivation factor, is not. We're not inferring quality from it. Going back to this, I think that was the motivation here. So trying to infer, if I remember rightly, there was fake news and non-fake news tagged as such in this paper. That was the data set, at least. The model, again, like ours, I suppose, abstracted that to a single number that was like a fitness in our case. But you're right. I mean, that's the real question is about quality versus fitness, but there's not necessarily one-to-one relationship there, I think, either. And that's a question for data-driven people as much as anything else. Yeah. Thanks.
More questions? Okay.
Thank you for the talk. I have a question about the branching process. So as far as I understand, you don't say, so for each process, you have, you don't have the topology of the network in the network of Twitter network. So what I'm guessing that maybe your model, I mean, it's working quite well with the data because it fits the data very well, right? But somehow you are not taking into account the topology of the Twitter network. So you're saying that that every node somehow sends some information to the neighbors, but they are independent on the neighbors that have in the network actually. So I don't know if you.
No, you're right. I understand the question, and I wasn't very clear, I think, here. So let me see if I can. Oh, that's possibly me. Let me plug this out again. So you're right. I didn't say where the branching process needs an offspring distribution. The model is built on a network, right? So what's the connection?
Yeah.
Essentially, the out degree distribution of the network is the backbone for the offspring distribution. So if I'm a user and I tweet something, the potential children are the followers of me. Mm-hmm. So it's basically related to this PK. Now there's some. So for example, we have variants in the model where not everybody accepts the information and therefore retweets it, etc. But it's to do with you can think of the Twitter network giving you a backbone, and on that backbone network, the offspring distribution is the branching process is the offspring is based on the offspring distribution. So this PK, which is the network out degree distribution, plays in the branching process plays more or less the role of the offspring distribution.
Okay, so exactly. So my question was where this PK enters in the branching process.
Yeah,
This is
that's
true.
so almost directly is the offspring distribution is the short answer. There's a slightly more long answer, which is to do with in this paper with Ymir, for example, this one. Yeah, you can see there's a joint distribution of in and out degrees, for example. So we did allow for that. In one case, you might take your real Twitter network, count the number of in degrees and out degree in links and outlinks for each node, give that a joint distribution, and then feed that in. So there is an offspring distribution, which is slightly more complicated than just the offspring distribution, but still is more or less dominated by it. In particular, the tail behavior is this happens whenever the out degree distribution has a infinite variance tail, and this happens whenever the out degree distribution has a finite variance tail. I think it's fair to say.
Okay. I was surprised because also, you feed the data very well, just a very, very simple process. So
This isn't data, just to be clear. This is simulations in theory, but yeah, the data. The one case we did do some data fitting. Where's it gone now? This one, yeah, did fit pretty well. Yeah, but mostly what I've shown you is simulations versus theory. So don't think we're better than we are. Yeah.
Thank you for the talk. It was very interesting. But my question is, I mean, where is the algorithm, the Twitter algorithm? So, because it's an algorithm that decides what is showing to you. And I guess it's not equal to show you one meme that has been retweeted just once. And it will be more likely that it shows you one meme that has been retweeted like 100 times.
Yeah, that's a very good point. I should say we did most of this work before that became a common thing in the Twitter algorithm. And I know people are trying to absorb that in. I think if you increase the probability of a meme being retweeted on the basis of whether it's been retweeted or not before, getting power law distributions of popularity is a different model. Yeah, but again, not necessarily claiming this is a model of reality. Just it's an interesting model in which I suppose the point of interest is not to be predictive, but to point out that some very, very simple, surprisingly simple models where, for example, everyone has 10 followers, that's not Twitter either, but it still produces qualitative characteristics that you might assume you needed other things for. So you might assume you need the Twitter algorithm in order to produce viral memes, for example. This says you don't. Okay, now it doesn't say what happens in the actual Twitter case either, I grant you that, but yeah, yet another extension that we need to try and add. Thank you.
More questions?
Regarding the data, okay, your model gives you a power law up to some point, except for the tail, if I understand right. So there's a power law.
Except the tail.
Yeah,
So
except for the tail, yes.
Yeah.
And then, okay, you showed just one picture in a moment with empirical data where it was kind of, let's say, but not very. Yeah, this one here, just okay. I don't know, 2 orders of magnitude maybe.
Yeah.
Well, okay. There's the slide you showed from the Nature Human Behavior paper. This was also this kind of data because I wasn't sure.
I think it is the same kind of behavior, yeah.
But then there's if I remember right, there's a curvature in the data. So the black line that corresponds to the actual data, not to the model, has a curvature all the way. So the question is whether we should be looking for a power law or whether there's something completely different there.
Yeah, good question. There we go. This one you're talking about?
Yeah, this one. Yeah, this one. Yeah, if you magnify it, the black line, which corresponds to the empirical, it's apparently curved.
Yeah, there is a
Of course, if you would plot, I mean that the curve minus diagonal would be much easier, better to see it, but still there is a curvature.
Yeah.
So do we really want to have a power law there, or maybe not?
No, that's fair. And interestingly enough, if you mix so the reason I was motivating this is because if you put in heterogeneous fitnesses, you actually get a mixture of distributions, and it's the mixture of distributions that fits to this rather than each individual distribution. So this probably is actually more like a -3/2, and then the combination of the exponential tails for the relatively unfit and the relatively fit ones is such that the combination of all those exponential tails, and that's really the point of this, or the point they make in this paper, can give you something that asymptotically gives you -2 power law in a certain range, not everywhere, but in a certain range. I don't know if that was your point, but that's, yeah. You were that the,
I'm suggesting it's just no power law in there. I mean, at least not. in
oh,
this
maybe it's not
data.
power law at all. Well,
Yeah,
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 I
so
mean,
if you're trying to fit a model
I'm
which
never
gives you a power
brave
law-
enough to claim power laws on anything. So it's a,
Well, okay. Well, you showed pictures from your model
yeah,
saying that
yeah,
there
that's
is a
because I
power-
could prove those. Yeah, yeah, yeah. Except where I can do the asymptotics that says it's power law. I definitely won't claim it from data. And yeah, here you're right. It's ambiguous enough. Yeah, probably enough to say for now.
Any further questions? No, I was curious about the number of memes present in the system at a given time,
Okay.
especially in terms of your innovation. I mean, what would happen? I mean, in your innovation, you create a new meme at random, but there is no limit in the different memes that you can create.
That's right.
What happens if there is some restriction on the possible number of memes or?
Well, what do you do in an innovation event then? You repeat one of the existing ones, maybe?
I'm thinking mathematically, not in.
I know,
terms of
yeah.
motivation.
The number of memes in the system grows kind of linearly in time, right? So because there's a constant rate at which innovation happens. So the number of memes that were ever alive in the system grows linearly in time. But remember, memes die as well. So there is a steady state number of memes that are currently alive in the system, which actually I don't think I've ever calculated, but that's a good question. But it does reach a dynamic equilibrium, so there should be such. And you're saying if there was a maximum meme index or something that we couldn't go beyond, what would
Well,
happen?
you could only, I mean, it would not call it should not call an innovation, but if you are only allowed to randomly change to a meme that is present in the system.
Never thought of that. That's
I
a good
was
question.
thinking of the difference between what you call innovation or just random changes.
Okay.
You are not receiving something, but you randomly change.
Yeah, I
So
suppose one important thing is when we call an innovation event, we start a new tree.
Yeah.
And if it was a rediscovery, let's say, or whatever we call it, it would be adding to an existing older tree.
It's a random
Which is a different question, but
random
an
change
interesting
of
one.
state.
Yeah. Random rediscovery or something. Yeah.
Okay, then let's thank the James again.
Thank you.
Now we have coffee and cookies outside, and at the 3:45 we have our second seminar.